Okay, let's talk about a device called a capacitor. To understand a capacitor, you need to know what capacitance is. And capacitance is the ability of a capacitor, which is the device we're going to talk about, to store charge on its plates. We're actually talking about storing charge in a circuit now, which is something new. We haven't discussed that before. The units are going to be farads, and you see that right here. And we're going to see how that's calculated. Capacitance is C, and it's calculated by the amount of charge we can store per volt. Okay, so that's how we find that. So let's talk a little bit about that and look at a calculation that might help you see it a little bit better. Let's say we have a capacitor with a value of 1 microfarad. Okay, and we have a voltage that we're applying to that capacitor. We want to store about 10 volts. All right, so what we're actually storing, we're storing voltage across the capacitor, but we're actually storing charge. Okay, so in order to find that charge that we're storing, remember Q from before, that's charge, and it's measured in coulombs. Okay, remember, and coulombs are what? They're just a lot of electrons, okay? So let's talk about coulombs here. We find how much charge we're storing on the plates of this capacitor by multiplying the capacitance by the voltage. And so I've got a 1 microfarad capacitor, and I'm going to multiply that by the 10 volts that I would like to store on that capacitor. So that means we're going to have about 10 microcoulombs of charge stored across the plates. And again, what is that? That's really just electrons. Okay, so if I take the 10 microcoulombs and multiply that by our 6.242 times 10 to the 18 electrons, let's see, electrons per coulomb, we see that that is a lot of electrons, right? 62.42 times 10 to the 12, I think, electrons. Okay, so that's how much, that's the charge that we're storing on the plates. Now, you will practice with that equation a little bit later. Okay, so what is actually happening is when we take our capacitor, and this right here is what we're going to call our capacitor. I'm going to circle that for you. We've got these two plates of our capacitor of some sort of material that will allow that charge to store, and then between the two plates we've got some kind of material in here, okay? If you can imagine, between the two plates. In this case, we're told that there's an air gap, all right? So that means that the dielectric material, and I'm going to draw in what we've got here, the material between the plates we actually call that the dielectric, or dielectric material between the plates. So we've got that to consider in our capacitor construction. Another consideration is the area of the plates themselves. How large are they? Is this a 1 centimeter by 1 centimeter? Or a meter by a meter? Like, how big are those plates? Because the larger the plates, the more charge we can store on those. So these are two considerations in the construction of our capacitor. Okay, we have the area of the plates. We have the material between the plates. We call that the dielectric material. And the third thing to consider is right here. It's how much distance do we have between the two plates? Okay. Because remember, when we're talking about storing charge, okay, we're talking about basically an electric field, and the field strength is going to vary depending on how far those plates are apart, okay? The closer they are together, the stronger the field of attraction between them, just like you take a magnet and you get it really close to the refrigerator. You feel that force stronger the closer you get it to the refrigerator. The closer these plates get, the stronger that force of attraction and the more electrons we can store. The area of the plates, the larger the area of the larger the plate, the greater amount of charge we can store. And the material, if we have a material that helps us set up a stronger electric field, that's also going to help us store more charge. Okay, so as you know, that all boils down to an equation for us, and here it is. The capacitance of a capacitor can be calculated by taking the permittivity, and I'm going to highlight some of these for you. The permittivity of the dielectric, okay, that's the dielectric material there. The permittivity times, so we did permittivity, times the area, that's the area of the plates, okay? Divided by the distance between the plates, okay? So, divided by the distance between the plates right here. So what this equation is really saying is that if I have a greater distance between the plates, then that means that I have a lower capacitance, or I can't store quite as much capacitance. I can't store quite as much charge on the plates. If I increase the area of the plates, I'm actually going to be able to store more electrons, okay? And if I increase the dielectric, or the permittivity of the dielectric material, then that's going to help me store more electrons as well. Okay, so let's work with this equation just a little bit. Before I do, I want to call your attention to the fact that we have actually in our second equation here, if you look at this equation, we have area, just like we did before, and the distance between the plates. But we also have two permittivities to talk about, okay? It's really just one permittivity here that we're discussing, okay? But the permittivity of the material is actually the permittivity of air times what we call the relative permittivity of the actual material. That means there are some materials that might have twice the permittivity of air. So we would just take the permittivity of air here and then multiply by 2 for the relative permittivity. Or the material might have 3 times the permittivity of air. Again, we're going to start with the permittivity of air, which we know, this is a known number, it is 8.85 times 10 to the negative 12 farads per meter. And then we're going to multiply by whatever the relative permittivity is for that particular material. Okay, so let's go back to our practice problems here, okay? We're going to go to, sorry about that, we're going to go to how much charge is deposited on the plates of a 0.15 microfarad capacitor if 45 volts are applied across the capacitor. Okay, that was that first equation we had all the way up here where we found that charge is equal to capacitance times voltage. All right, so let's apply that equation here. So we've got 0.15 microfarads times 45 volts. And that gives us 6.75 microcoulombs, sorry about that, microcoulombs of charge will be stored across that plate. Now, if at any time you want to practice this problem yourself, before I do it, just hit pause on the video, work the problem yourself, and then hit play on the video. If you want to back up, I mean, the nice thing about having the video is you can go over this as many times as you want, and you can kind of skip around if you want to do that. Okay, so that was our first equation. Now let's talk about how we're calculating the capacitance of a capacitor up here. Let's work on a couple sample problems of that. So in number 2, we're going to find the capacitance of a parallel plate capacitor if the area of each plate is 0.1 meters squared and the distance between the plate is 2 millimeters. Now, be careful because note here we've got millimeters, okay? In our equation up here, the distance between the plates is measured in meters. The area, it needs to be meters squared. So if you have meters squared, you're good, you don't have to do anything with that. If you have millimeters, remember, millimeters is 10 to the negative 3 meters. So you're going to have to incorporate that in your equation. And then it tells us that the dielectric of air is 8.85 times 10 to the negative 12. So the dielectric in this parallel plate capacitor actually is air. Okay, so let's use our equation. And I'm going to actually switch to the second equation where we use the dielectric of air times the permittivity of air times the relative permittivity times area over distance between the plates. So we've got 8.85 times 10 to the negative 12. The units were farads per meter. The relative permittivity is 1. 1 because the dielectric is air. Okay? And then the area is 0.1 meters squared. And the distance between the plates is 2 millimeters, or 2 times 10 to the negative 3 meters. Okay? You want to plug all that into your calculator, and you should get 442.5 times 10 to the negative 12 farads. Okay, now this is going to be a cause for you to learn some more of your prefixes that we might not have seen before in the class, but 10 to the negative 12 is actually pico. I hit 21. Okay, 10 to the negative 12 is what we call pico, and we use a small p for that. So this is 442.5 picofarads. Okay, and there's your answer. When you're working on any kind of homework problem, you want to kind of put a box around your answer just to make sure that your teacher sees that you indeed know where the answer is. Okay, next, let's try this again. So we're going to work with the same capacitor. So the capacitance for the same capacitor here for number 2. But this time we're going to use paraffin-coated paper between the plates. All right. So your textbook has a chart of relative permittivities. I'm going to tell you here that the relative permittivity of paraffin paper is actually, let me see, 2.5. That means that paraffin paper has 2.5 times the amount of permittivity of air. Okay, so that's going to make a stronger capacitor just by putting in that dielectric material. Okay, so basically everything is going to stay the same. except that I'm going to put this 2.5 into my equation right here. Okay, so area over distance. So I've got 8.85 times 10 to the negative 12 farads per meter. Now times 2.5, 0.1 meters squared on the top, and 2 millimeters on the bottom. Okay, so what we get there is we find that that gives us 1.1 times 10 to the negative 9 farads, and 10 to the negative 9 happens to be nano. You probably have heard nano before. So that means we have a 1.1 nanofarad capacitor. So if you were to take the original capacitance that we found, you could have just multiplied it by this 2.5 and you would have gotten 1.1 nanofarad. So you didn't have to go back through the entire equation, but you can. There's nothing wrong with that. Okay. Now let's try one more iteration of this. We're going to find the capacitance of the capacitor from number 3, so the one we were just doing, but this time we're going to increase our area to 0.2 meters squared, and we're going to increase the distance between the plates to 3 millimeters. All right, so let's do that. I'm going to use the same equation here. We've got our permittivity of air, our permittivity of the paraffin paper, relative permittivity, times the area divided by the distance between those plates. So I've got the 8.85 times 10 to the negative 12 farads per meter times my 2.5 for the relative permittivity of paraffin paper times, this time we've got 0.2 meters squared for the area, and the distance is now 3 millimeters instead of 2. Again, keep watching those prefixes, all right? And this should work out to 1.47 times 10 to the negative 9 farads. And remember, 10 to the negative 9 equals nano, or little n, 1.47 nanofarads. Okay, so to review, what we talked about in this video was, first of all, what a capacitor does. It stores charge, okay? And the storing of that charge, we call that capacitance. It's the ability of the capacitor to store charge. And we talked about how much charge would be stored depending on the capacitance of the capacitor and the voltage that we want to store across the plates. Okay, so then we discussed how to calculate that capacitance. Remember the construction of our capacitor up here? We have 2 plates that are in parallel with each other, and we are going to see an accumulation of negative charges on one of the plates and positive charges on the other. We'll talk about that in the next video. But the construction of the capacitor, we have the area of the plates. The larger the plates, the more charge they can store. The distance between the plates right here. The further apart, the less strong that connection is going to be, so we're going to store less charge as we move them further apart. The closer they get together, the more charge we're going to store. And then the material between the plates. That is also going to be a determining factor and will tell us how much charge we can store as well. And then we work through those problems. In another video, we will talk about exactly what happens in the circuit when we put a capacitor in the circuit. This was just talking about the actual capacitor itself. A couple things to review as well. We gave you 2 new prefixes. You already had 10 to the 6, which is mega, or capital M, 10 to the third, which is kilo, which is K. 10 to the negative third is milli, or little m. And 10 to the negative 6, which is micro, or that mu character. We're going to add to that 10 to the negative 9 nano, small n, and 10 to the negative 12, which is pico, or small p. This should round out about what you'll need to know for the course as far as the prefixes. And that's all you need to know about capacitance for the day.